In this video, we will discuss the step response of the first order systems. We have a first order system. The transfer function is k over tau s plus 1. Now we want to calculate the step response. I will give you a few minutes to calculate the step response. You know the basic procedures is to first find the Laplace transform of the input signal. Then, based on the definition of the transfer function, the Laplace transform of the output is the transfer function times the Laplace transform of the input signal. Then we can use the partial fraction expansion and the cover-up method to calculate coefficient. Then we can use the inverse Laplace transform to find the time function. First, let's write the transfer function in this way. Let's divide tau on both the numerator and the denominator. So we have hs k tau s plus 1 over tau. Then we know the Laplace transform of the step signal is 1 over s. Therefore, the Laplace transform of the output is a product of the two. So here it shows the Laplace transform of the output signal. Then we can use the partial fraction expansion to write ys in this form. The last step is to apply the inverse Laplace transform. So we have k minus k exponential minus t over tau. So if you see here, the final value of the step response is k as t goes to infinity. Because the second term is 0 when t is very, very large. Similarly, we can define the time constant. So in the step response, the time constant is the time when the response rises to 1 minus 1 over e times the final value. Now let's put t to the time constant tau. Let's see the value of the output yt. So if we let t to be tau, then we know the y tau k minus exponential minus 1. That is k 1 minus 1 over e. So that's exactly the 1 minus 1 over e times the final value, because k is a final value. Again, the time constant is a metric of the speed of response. So we can see the plot on the right. This plot, it shows the step response. Here, it shows the impulse response. We know for the impulse response, so the time constant is defined as a time when the impulse response decreases to 1 over e of its initial value. Here, let's focus on the step response. We use the time constant to measure the speed of the response. So this plot is drawn with the value k is 1, k is 1, and tau is 1. So after one time constant, the response reaches 63% of its final value. After two time constants, it reaches 86% of its final value. After three time constants, the response reaches 95% of its final value. So after four time constants, the response reaches 98% of its final value. So after 5 time constants, it reaches 99.33% of its final value. So in general, we will consider that after 5 time constants, so the response is at its steady state. So how do we use the result here? So we know it's very easy to calculate the impulse response and step response for the first order system. The use of the results here is to identify the parameters in the model. Now let me give you an example. Now let's assume we have a process. Then we don't know the process. We don't have a model for the process. We don't know the model is first order, or second order, or higher order. Then the first step we can do is to test the system. To test the system, we can apply a step signal. Then we can measure the output. Let's assume this plot shows the output when the input is a step signal. Then we will see if we compare if we compare this plot with the step response of the first order system. So we might think this step response is a step response of a first order system. Then let's see the final value. So the final value we'll see is 0.6. So the K in the standard form. So K will be the final value. Then tau is time constant. So we know for one time constant, so the response reaches 63%. Now let's calculate the 66% of the final value. This will be 0.4. So times to have final value times 63%. So then let's calculate. We have it's roughly 0.252. So let's assume here. Then we know roughly the time constant is 0.2. Then after 5 time constants, the response reaches the steady state. Therefore, we can calculate the parameter K and tau. So assume the K is 0.4 and tau is 0.2. Then to verify it, we can, assuming this is the transfer function, then we can simulate. If this is the input signal, we can simulate the output, then compare the output with the one we measured from the system. If they are very close, so we see here the transfer function, and the K is 0.4 and tau is 0.2. So you can think of the example of the motors. We know the motor from the voltage to the angular velocity. It is a first order system. So if you have a motor, then you don't know the parameters. Electric constant, suppose you don't know any of the parameters. So what you can do, you can apply the constant voltage and then record the step response. Then you will know K and tau, then you know the transfer function of the motor. So another use of the time constant, let's assume the hard drive disk control. Then if someone designs a control system, they say, okay, the time constant is 1 for the hard drive disk control. So immediately you know the design is not good. Why? Because whenever you need to read a data from a disk, you need to wait for 5 time constants for the response to reach the steady state. So for the needle to reach the right track on the disk. So whenever you need to open a file, you need to wait for 5 seconds. Then you know if the transfer function for the hard drive disk control, you need time constant be very small. You want the system respond faster. So we have some step response performance specification, but they're not usually used in first order system. They're usually used in second order system. But let me mention it here. Then we will discuss more details about the performance specification in second order systems. So the first specification is settling time. So the definition is a time for the response to reach and stay within 1% of its final value. Now let's use this as an example. It means the first time it reaches 99%. It's somewhere around here. It's 99% and stay within the 1%. So we know it's roughly between 4 time constant and 5 time constants. Now let's calculate the settling time. Let's use TS to denote settling time. The settling time will be when the YT is 99% of its final value. So the YT will be 0.99. So the final value is K. So that's the time when T is TS. So we know K exponential minus TS over tau will be 0.01 K. Then we can divide K on both sides. The K is gone. Then we can write 0.01 as 10 power of 2. Then we can apply log on both sides. So we have minus TS tau, and here on the right hand side we have minus 2 line 10. So then we can multiply -1 on both sides. So we know that twice the settling time will be 2 times log 10 times the time constant. So that will be the TS is 2 log 10 tau is roughly 4.6 tau. So TS will be some value here. 0.6 time constant. That's the settling time. The second performance specification is overshoot. So the definition of overshoot is the maximum amount of the system overshoots its final value divided by its final value. Now let's look at the step response of a first order system. So the response will never go beyond its final value. Therefore, the overshoot is 0. For the overshoot, we use MP. It is usually written in the percentage. We call it percentage overshoot. So the percentage overshoot for first order system is 0. The last performance specification is rise time. Rise time is a time for the response to go from 10% to 90% of its final value. So here is 10%. That's the T1. Let's denote when the response reaches 10% T1. So 90% is here. Then the rise time is defined by T2 minus T1. Now let's calculate. So T1 is YT is 10% of its final value. This will be 0.1 K. The final value is K. Then let's the T1 is equal to T1 exponential minus T1 over tau. Then we know here it is 0.K equals K exponential minus T1 tau. So let's divide K on both sides. The K is gone. And again, we apply log on both sides. So we have line 0.9 minus T1 over tau. Then we multiply tau on both sides. Then we multiply -1 on both sides. We know T1 is minus tau ln 0.9. Similarly, we can calculate, so T2 is the time for the response reaches 90% of its final value. So it will be, the calculations are the same. So here will be ln 0.1. So if we use T1, T2 minus T1, then we have ln 0.9 minus ln 0.1 times the time constant. So it's roughly 2.2 time constant. So from here to here, it's roughly 2.2. So the rest time, it shows the speed of response from a different perspective. Then the settlement time, it shows when the response will be settled down at a steady state.